fire-breathing fastest cars on land, to some of the most extreme engines on water, to the cutting-edge technology of today's hybrid automobiles. Horsepower has defined the way we move for 2 centuries. Is there really the power of 200 horses under your hood? Find out now as we rev up for horsepower on Modern Marvels. For some, faster has always been better.
Speed's very addictive. It can make you do things that some normal people wouldn't want to do.
When they step on the accelerator pedal, they want the vehicle to move. They want it to go fast. They want the feel of raw horsepower.
And nowhere can you find more raw horsepower than on a Sunday afternoon at the drag strip. These are the fastest accelerating vehicles on Earth. Top fuel dragsters and their counterparts, known as funny cars, can rocket to speeds of more than 300 miles per hour while scorching a quarter-mile track in under 5 seconds. They are power-driven by supercharged engines of up to 8,000 horsepower. Surprisingly, in this testosterone-fueled sport, one of the top handlers of horsepower in the country is a woman, Melanie Troxel.
The car doesn't know whether there's a male or female in the seat. It's, you know, equal all the way around for all the drivers. When you're talking 330 miles an hour, 8,000 horsepower, I mean, it's such an animal, these cars. Everything out here is about horsepower. Speed, elapsed time, it all comes down to horsepower.
Astonishingly, once stripped of their massive air intake funnels and exhaust pipes, at their core, these engines aren't much different than those of the high-performance 8-cylinder sports cars on the road today. The difference is what goes into the engine.
The secret to making between 7,000 and 8,000 horsepower on one of these 8-cylinder engines is the fuel. We pour nitromethane into the fuel tank. We distribute it with a massive fuel pump into the engine. We put the air into the engine through an injector, which has got a supercharger under it. It sucks all the air into the engine. We mix those two in each cylinder. We light it with a big magneto, and that's what makes all the power.
Nitromethane is like gasoline on steroids. To give it an explosive boost, the fuel supplies its own oxygen atoms to make it burn at an accelerated rate. 15 pounds of air is needed to burn 1 pound of gasoline. Nitro needs less than 2 pounds of air to burn 1 pound of fuel. This means 8 times more nitromethane can be pumped into a cylinder. The more fuel burned, the higher the horsepower. In 1 quarter-mile, 5-second run, a dragster will burn up to 15 gallons of nitro. That's a 60th of a mile per gallon. If you're looking for fuel economy, this isn't it.
Nitromethane over the years has proven to be a very powerful fuel. We've learned to tame it and put it into these engines to make the maximum amount of horsepower with the air ratio that we have.
But nitromethane is also extremely volatile. As Melanie Troxel discovered when her engine exploded during a race. Luckily, she escaped without injury and even won the race. But close calls carry an extra burden for Melanie and Tommy Johnson Jr. They face risks not only as drivers, but also as husband and wife.
Safety concerns, we both know what can happen, the ultimate price you might pay, and we both accept that, and you understand that. All right. We'll look later.
Married in 2001, this couple is driven by the thrill of speed and competition. But because they've never raced each other, the question remains, who has better command of this immense horsepower?
Well, you know, they say women have better reaction times, actually, in these cars. So if that's any indication, I'm pretty sure that I'd beat him hands down on the track.
I'm going to beat her just like anybody else out here.
Drag racers like Melanie and Tommy back up their bravado by harnessing as much horsepower as possible. But oddly, like a lot of us, they have trouble defining what horsepower actually is.
Horsepower is a tough question to answer.
Well, it's the power of one horse, right?
Most people don't realize it, but there is an exact definition of a horsepower, which is 33,000 foot-pounds per minute.
If you didn't quite get that, don't worry. Just remember that horsepower is work done over time.
I've got about 100 of you under my hood, yeah.
But you may wonder where the horse comes in. In the late 1700s, James Watt was the struggling inventor of a new type of steam engine, and also a savvy salesman.
And since his customers were basically using horses to do their work, he needed to be able to tell his customers, look, I have a steam engine here that'll replace 2 of your horses or 4 of your horses. And in order to do that, he had to actually go out and watch a horse.
There are a few theories about how James Watt created the concept of horsepower. According to the most popular one, he observed a horse on a grinding mill wheel. It was something like a horse on a device we know today, a hot walker, used to cool down horses after a workout. However, the horse Watt saw met resistance when connected to the grinding wheel. Watt calculated that the horse pulled with a force of 180 pounds. He multiplied that by the horse's speed, which he determined to be 181 feet per minute. After rounding up the number, Watt arrived at nearly 33,000 pounds, lifted 1 foot per minute. And voila, he'd defined horsepower as work done over time. How does this translate into horsepower for a car engine? Here's how it works. An internal combustion engine ignites a combination of fuel and air. The explosion drives a piston downward. The piston's movement turns a crankshaft. The amount of turning force on the crankshaft is known as torque. An example of torque is when a wrench is used to loosen a nut. The more force or torque applied to the nut, the easier it is to unfasten. So horsepower is the turning force of torque, measured in foot-pounds, combined with a number of crankshaft rotations per minute. This is work done over time. And again, one engine-generated horsepower equals 33,000 foot-pounds per minute. How do humans stack up in horsepower generation? The average person can sustain only about 1/10 horsepower when riding a bicycle. Of course, a world-class biker like Lance Armstrong would do better, but he'd only maintain about 1/4 horsepower. But no matter how strong a rider is, there's only so much a human can do.
We get tired, we go slower, and eventually come to a stop. We just don't have the stamina. We don't have the endurance of a mechanical machine.
Mechanical horsepower became a key selling point for many car makers. From the early 1900s with the Ford Model T at 10 horsepower, to the muscle cars of the 50s, like the 283 horsepower Corvette, to today's Saleen S7 at a monstrous 750 horsepower. The car industry has sold customers on ever-increasing amounts of horsepower. And yet, there was a problem. From the beginning, manufacturers measured their own horsepower. So who was keeping the auto industry honest? In 1917, an organization called the Society of Automotive Engineers, or SAE, provided a set of horsepower testing standards.
Back in the early days, they used a very different process from company to company, from tester to tester. What SAE standards tried to do was to establish one formal way of running the test.
From its inception until today, the SAE has tried diligently to make horsepower a measurement car buyers can believe in.
We look at horsepower. If a number is stated as SAE certified power, that customer has a level of assurance that that's the real number as tested and as tested properly.
Here at a General Motors facility outside Detroit, Michigan, technicians are testing an engine to ensure it performs up to the 310 horsepower they'll advertise to the public. Millions of dollars are riding on the results.
It's a little nerve-wracking. There's a lot of responsibility involved, and there's a lot of things at stake, so I hope everything runs smoothly, and I look forward to running it.
An instrument known as a dynamometer is used to measure the horsepower of the engine.
The engine is mounted to the test stand. It is then connected through a drive shaft to our engine dynamometer. The dynamometer is what actually measures the output of the engine, measures it in horsepower. The parameters of the dynamometer are then measured and recorded in the engine control room.
The dynamometer measures horsepower by recording the torque and rotations of the crankshaft. The crankshaft is attached to a rotor inside the dynamometer. As the rotor spins, an electromagnetic field makes the outside hull of the dynamometer want to turn in the opposite direction. To measure torque, an arm exerts resistance force on the dynamometer hull, keeping it from turning.
Out here on the outside, we have the dynamometer torque arm. The torque arm is nothing more than a load measuring device. This load cell down here at the bottom measures the force exerted, which resists the twisting of the dynamometer as it measures the power.
Car manufacturers still test their own engines. But since 2005, SAE has required that horsepower tests be carried out under the watchful eye of an official witness. If a manufacturer wants to earn the Society's certification, General Motors does this on a voluntary basis.
How are you doing?
Pretty good. I'm the conscience of the manufacturer. I make sure that the test is run correctly according to the procedure, and that the certified numbers will be the numbers that will be reaching the public.
With everything in place, this all-important test begins.
Everything looks pretty good, and we're ready to start the test. Let's go.
Only a few minutes into the test, technicians detect a problem and stop the procedure to investigate.
Just a slight rattle at certain speeds, which isn't normal. It could be a loose pin, something wrong with the prop. We'll check that out.
With the witness watching, the GM engineers need to fix the problem fast.
After inspecting the prop shaft, we noticed that the guard was a little bit loose. We then made sure all the bolts were tightened on the prop shaft, to make sure all the bolts are tight, and now we're ready to go.
With the problem solved, the test continues. For the next 5 hours, the engine undergoes an exhaustive examination.
Okay, that was the last test point. Everything looks good. Go ahead and start the engine shutdown sequence.
With the test completed, the question is, did the engine make the targeted 310 horsepower the manufacturer wants to claim? It's a tense time as the engineers and the witness pore over their calculations.
It was a valid test. All the test parameters were within spec. We have good horsepower numbers, so it was a valid engine power test, and we can certify.
Thank you very much.
Thank you.
This is just one of the many engines General Motors has tested under the new SAE standards. Of course, the measure of horsepower isn't just for land. Some of the most extreme and volatile horsepower engines move on water. Inventor James Watt's first steam engines produced 6 horsepower. Within 20 years, his engines delivered as much as 190 horsepower. Horsepower will return on Modern Marvels. They're 3-ton boat beasts, careening across the water at speeds exceeding 200 miles per hour. Their powerful turbine engines generate up to 3,000 horsepower. This is the world of hydroplane racing. Dave Vilwalk holds one of the world hydroplane speed records at 220 miles per hour.
These are a 3,000 horsepower bucking Bronco. Everything about it's difficult to control, and a lot of times you're not in control. We just try to do the best we can.
These craft half skim, half fly across the surface of the water. Only the propeller is underwater as they throttle to full speed.
A hydroplane is part airplane, part boat. On my right foot, we have a throttle pedal that controls the engine throttle. On the left side, we have a flight control pedal, which controls a forward flap that either makes the boat go up or down. So we're flying the boats like you would an airplane, just very, very close to the water, hopefully.
Hydroplane racing is a summer sport. During the off-season, the boats and engines go through a complete overhaul. At the Turbine Engine Warehouse near Seattle, Washington, this engine is fired up to assess that all 3,000 horsepower will function for the next season. They don't call them thunderboats for nothing. The extreme noise is deafening. Although it may sound like a jet engine, it doesn't provide thrust, but rather rotation.
We have rotors that are spinning anywhere from 18,000 revolutions per minute to 15,000 revolutions per minute for the power turbines. The turbine engine makes horsepower in 4 stages: intake, compression, combustion, and exhaust. And that makes a very efficient engine.
In stage 1, the turbine engine takes in air at 300 cubic feet per second. Stage 2, the air goes through a compressor, which pressurizes it to 90 pounds per square inch. Stage 3, the air is combined with fuel in the burner can and is ignited. And finally, stage 4. The supercharged hot gases spin the main turbine assembly.
This is the power turbine assembly. This is where the horsepower is made. Hot gases that are about 1,500 degrees Fahrenheit push on all these little blades. There's lots of gas, lots of little blades. And this wheel is just like a pinwheel. All these little blades are at an angle. It spins this power turbine assembly 15,330 revolutions per minute. It turns this shaft the same speed. The shaft is attached to the propeller, which pushes the race boat forward. And that's what gives the hydroplane its tremendous speed and horsepower.
With all this explosive horsepower, you might think the engine needs highly combustible fuel.
Everybody thinks that we use exotic fuels in these engines, but we don't. What we have is basically home heating oil, which is essentially kerosene. We use kerosene because it's a very stable fuel. The risk of fire in the boat is very low. And also we can extract a lot of energy out of every gallon of fuel versus a lot of other fuels.
It's one thing to harness 3,000 horsepower on land, but it's quite another on the ever-changing surface of water. Drivers are put to the ultimate test.
You're essentially an accident waiting to happen. When you're going so fast, you cover a football field in a second. So when you're looking for something to happen, you're looking way down the track.
Ken Muscatel is a hydroplane driver who lost his battle with horsepower in a spectacular crash.
The boat was going good, about 185, not super fast, and all of a sudden it just starts lifting. And it's not coming down, and it goes higher and higher and higher, probably ended up 60 feet in the air, flew all the way around 360, landed on its tail, slapped down back on the water, broke the boat in half, but was kept going, so I had to shut it off, and I just waited for people to come. I felt lucky to be alive. Lucky not to be hurt, and still disappointed because we weren't going to be able to race the boat.
So with all the speed and danger, have hydroplanes reached the outer limits of horsepower?
The bottom line is, in the future of hydroplane racing, I see more technology, more power, faster race boats.
But high horsepower on water doesn't always mean high speed. It can also determine sheer muscle. One of the most powerful diesel engines in the world is the Wärtsilä RTA 96C, with an astounding 95,000 horsepower. This behemoth was designed to power mammoth ships, like the Costco Long Beach, a 72,000-ton cargo container ship. Manufactured in Korea, the Wärtsilä is 76 feet long and 44 feet high, as large as a 3-story house.
I've been working on big engines all my life. This is the biggest. It's amazing. It's a challenge. It's a lot of horsepower to look after. It's a big engine, massive.
The total engine weight is 2,300 tons. The crankshaft alone weighs 300 tons. It's over 1,000 times more powerful than many car engines. Each of the Wärtsilä's 12 cylinders delivers 8,000 horsepower.
This is a spare piston for this main engine. It's 20 feet tall and it weighs 5.5 tons. Just imagine this piston moving up and down the engine at 102 times per minute. That's incredible.
Inside the 12 assembly units, where the pistons are connected to the crankshaft, technicians inspect the engine parts. Running at full power, the Wärtsilä would be far too dangerous to approach this closely, so it's slowed down to a fraction of its normal speed.
We are slowly turning the engine at the moment, just to give you an idea of this massive piece of steel coming up, driven from the pistons. When this machine is in operation, you will never be able to stand in this area.
However, using time-lapse photography, we're able to speed up the process and bring the engine to life. With each stroke of the 5.5-ton assembly, it covers more than 8 feet. This enormous mass of metal drives the crankshaft, which generates the 95,000 horsepower. The engine consumes up to 250 tons of fuel a day. It can propel the Costco Long Beach at up to 24 knots. A blazing speed for a container ship this size.
It gives you a feeling like a car driver. If he has a fast car on a good road without speed limit where you can use this horsepower. So it is a nice feeling.
Because of the rising demand for global shipping, bigger and faster ships are sure to follow. In the future, ship engines could pack up to 115,000 horsepower. Propulsion isn't the only use for tremendous horsepower. It's also harnessed to generate electric power. When the lights go out, people's lives depend on these monstrous engines. Since the 1980s, most hydroplane races have been won by boats using a turbine engine originally designed for Vietnam-era Chinook helicopters. Horsepower will return on Modern Marvels. Welcome to Waukesha, Wisconsin, a tranquil, unassuming town in Middle America. However, it's also home to incredible horsepower. Here at Waukesha Engine.
Many people have maybe never heard the name of Waukesha engine, but it's out there producing power throughout the world.
In this 1 million square foot factory, more than 800 workers design, build, and ship mammoth engine generators that deliver essential electric power around the globe. One of the largest in the world is the Advanced Power Generation System, or APG 3000, which produces 4,400 horsepower.
Waukesha engines are about horsepower, pure and simple. The way that we get that horsepower is we throw a lot of iron at it. The pistons are bigger, the block is bigger, the connecting rods, everything's just bigger, beefier to handle the durability and reliability that the customers demand.
The APG engine is 11 feet high and 25 feet long, and it weighs in at a massive 40 tons. It's a big engine with an even bigger job to perform.
The customers that buy these engines are in very critical applications. In a lot of places, we are their only source of electricity, be it in foreign countries where there is no electrical grid, be it in hospitals where if there's a power outage, they cannot go down because people's lives often depend on these engines operating reliably for as long as they can.
These engines use an internal combustion system that employs pistons connected to a crankshaft, much like in a car. Besides the size, the biggest difference is the fuel. Instead of gasoline, the APG runs on natural gas.
Natural gas is a very clean-burning fuel and very friendly to the environment, much more so than gasoline. It's very plentiful around the world in remote locations, so it's easily available, and it's definitely becoming a fuel of the future.
The APG can draw natural gas straight from ground deposits, or even draw methane gas from a garbage landfill. It always has a steady supply of power and never has to be refueled. This combination of engine and generator is known as an enginator.
The enginators are designed to last for years and years. Most of the major components last for the lifetime of the engine.
Construction of the APG begins when raw stock from an iron foundry is delivered. It'll take up to 4 weeks before the 8,700-pound crankcase and 3,700-pound crankshaft reach what is known as engine tolerance.
Tolerances are how close these parts fit together. They have to seal a lot of pressure from combustion, and there's a lot of moving parts. And because you're going through so many cycles, it's important that their fit be extremely close.
The crankshaft is hauled onto a computerized lathe, where almost a quarter of its size will be shaved off.
We'll be removing 600 pounds from this crankshaft as it's processed down the line. We'll be finishing those diameters down to the width of a human hair. We need this exacting tolerance in order for the engine to operate properly in the field.
The main part of the engine, the crankcase, undergoes a process known as machining, in which computer-assisted cutting tools drill cylinders for the pistons that will eventually be installed.
We machine off over 1,500 pounds to get that piece of iron into the dimensions that we require for quality.
The 42-pound pistons also go through the machining process until they shine like jewels.
These are aluminum pistons, and when you machine them, they get the shiny appearance, but don't let that fool you. When these are in operation in the engine, it's a very harsh environment. When you have this combustion, this huge explosion that goes on in the cylinder, this piston has to withstand that pressure, which can be as high as 2,000 pounds per square inch. And that's what creates your horsepower that's transmitted out the crankshaft.
When all the main engine parts are ready for assembly, they're placed on a rollover. It's something like an enormous engine rotisserie.
On the rollover that you see on the assembly line, where the crankcase is first mated with the crankshaft and the other major components, you're really looking at the birth of an engine. That's where it all comes together, and that's where it starts its life.
last stage for the APG engine is a break-in test.
It's a 5-hour test. We gradually increase the speeds and loads. This allows us to break in the components. Remember, there's many tight tolerances that need to be carefully broken in so the product will last a long time.
And maybe there's still greater horsepower to come from these Waukesha giants.
Horsepower will get higher in steps, but in order to get there, the engineers will have to look at things such as new metals, new controls, new emissions technologies to get that horsepower up to, say, 15 to 20% higher out of the same weight of iron.
Although technology promises to squeeze more horsepower from gas-fueled engines, another power source constantly provides millions of horsepower. And it's in abundant supply: falling water. Waukesha engines are painted bright orange and roar while operating. These features have earned them the nickname Thunder Pumpkins. Horsepower will return on Modern Marvels. Today's space shuttle rocket, at takeoff, delivers more than 1 million pounds of thrust, which translates to about 37 million horsepower. But that pales in comparison to the most powerful engine ever built, the Saturn V rocket. This behemoth flew a generation ago and sent American astronauts to the moon. The Saturn V produced 7.5 million pounds of thrust, which converts to an unbelievable 160 million horsepower. This enormous horsepower was used to break the bonds of gravity. But if we turn the equation around, gravity itself can be used to unleash an astronomical amount of horsepower. At Hoover Dam, on the Nevada-Arizona border, falling water has been harnessed to produce more than 2 million horsepower.
Water is heavy, and when gravity tries to pull water down, I think about 3,200 cubic feet per second dropping from the top of Hoover Dam to the base of the dam. And most people can see that that's kind of like the energy of a freight train.
Completed in 1936, Hoover Dam stands at 726 feet and is still the tallest concrete dam in the Western Hemisphere.
It's 45 feet thick at the top. It gets a little bit thicker at the base. It is 660 feet thick at the base, thicker than 2 football fields long. It's 3,250,000 cubic yards of concrete in the dam, and it weighs in at 6.6 million tons, enough concrete to make a 2-lane highway from San Francisco to New York City.
By holding back the mighty Colorado River, the dam generated Lake Mead, which is close to 500 feet deep and holds over 9 trillion gallons of water.
The big picture is the water starts out in Lake Mead, high up on this structure, right near the top. The deeper down in that water we go, the higher the pressure. We deliver the water to the turbines at a pressure of 250 pounds per square inch.
At the bottom of Hoover Dam are 17 reaction turbines. Each turbine produces between 150 and 180,000 horsepower.
The way a turbine works is like one of the old-fashioned sprinklers that brings the water up the center column and then across the top of the sprinkler. When the water shoots out of the angled nozzles, the sprinkler spins the other way. And that's identical to a reaction turbine.
A massive steel and copper shaft delivers the horsepower from the turbine spinning below to the generator, which produces the electricity.
I'm standing on top of a generator. This generator weighs 1.2 million pounds, and you can see it spinning. That shaft is spinning 180 RPM, or 3 times per second. So as you watch that shaft spin, You're watching the top end of 1.2 million pounds of rotating copper and steel. The purpose of this generator that we're standing on is to convert that horsepower in the water that's flowing into the turbine into electricity so that we can send that electricity out on the wires to our customers in the cities.
The horsepower that drives the generators can produce more than 2,000 megawatts of electrical power at full capacity.
That's enough to power anywhere from 300,000 homes to 1 million homes.
Most of our electricity actually goes to Southern California. We're one of the main reasons that Los Angeles is able to keep its lights on.
Thanks to horsepower created by falling water, the city of angels glitters. But to quench the thirst of Los Angeles, California requires enormous horsepower to drive water in the opposite direction.
It's called the Big Lift, and what it does is it moves that water 2,000 feet, a third of a mile, over the Tehachapi Mountains.
The Edmonston pumping plant, north of Los Angeles, moves 2 billion gallons of water a day. It's the largest water lifting system in the world.
The plant essentially takes the water and through 14 pumps at 80,000 horsepower for each motor, pumps the water over the mountain range.
But why expend all that power to lift water?
The problem is, in the northern portion of the state, we get a lot of rainfall. In the southern part of the state, we don't have much rainfall. In addition, there's a lot of people in Southern California, hence the need to deliver the water from the north to the south.
Before a drop of this water falls from a tap in Los Angeles, it must travel more than 600 miles through a labyrinth of federal, state, and regional water systems.
It is here, bam, that the water hits a dead end, and we've got to get that water over those mountains. And to do that, we utilize the Big Lift.
The water begins its big lift upward at the base of the pumping plant.
This is the forebay, the size of a football field, where all the water accumulates. And down 72 feet are intake structures. That's where all the water goes to each of the pumps.
The electric pumps work on the principle of centrifugal force. As the water enters, a massive solid steel shaft is attached to 4 impellers that lift the water. The impellers drive the water up with close to 1,000 pounds per square inch of pressure. Enough to lift it a third of a mile up and over the Tehachapi mountain range. In all, this rotation mass weighs 140 tons. Horsepower, and lots of it, is needed to drive this mammoth pump.
This is the heart of the system. Behind this door is an 80,000 horsepower motor. You can just feel and hear the energy that's here.
The key to the 80,000 horsepower is the amount of electricity that is supplied. Each motor uses about 60 million watts of power, enough to light up 600,000 100-watt light bulbs. When all 14 pumps are working, the electrical power use is enormous.
The total plant capacity absorbs enough energy to actually light up a city the size of Sacramento in terms of residential households.
The Edmonston plant can pump up to 140,000 gallons a minute over the Tehachapi Mountains to millions of thirsty consumers.
Because of this motor and its high efficiency, Southern California does receive fresh drinking water every day.
Horsepower delivers many of our basic necessities. But how long can we depend on it? With non-renewable fossil fuels such as oil becoming scarcer and more expensive, new technologies are creating the future of horsepower. The amount of water flowing through Hoover Dam could fill as many as 27 Olympic-sized swimming pools in 1 minute. Horsepower will return on Modern Marvels. In 1 year, the United States consumes over 140 billion gallons of gasoline. With gas prices spiraling upward, the specter of diminishing oil supplies, and global warming, new sources of fuel and engines may provide necessary horsepower. Hybrid cars are one way to squeeze more horsepower from less fuel.
The basic definition of a hybrid would be using of two power sources to power the vehicle or move the vehicle down the road.
A hybrid system uses an electric motor to power a car from a standing start. When a driver needs more speed, a gasoline engine provides acceleration. With this dual power capability, engines use less gasoline. In the past, most gas-sipping hybrid cars have shown themselves to be amazingly efficient, but still have not been able to match the horsepower many consumers want.
When they get in a vehicle, they're always going to want to go fast. They're going to want to step on the accelerator pedal. They're going to feel that surge of horsepower under their seat.
But now, a new breed of hybrid has hit the market that combines high gas mileage and high horsepower. One of these is the Lexus GS450H, which boasts 339 horsepower.
We're combining both gas V6 engine power as well as the electric motors. The gasoline engine is rated at 292 horsepower. The electric motors are powered by the battery, which is rated at 47 horsepower, and we add those two together to get a total combined horsepower of 339 horsepower.
As we raise the hood, we see all the engine panels, all the covers that's over the engine compartment, and actually directing airflow in and around the engine to keep it nice and cool. We have a cover over the engine, and as I remove that, you're able to see a typical 3.5-liter V6 that you'll see in most any vehicle. The difference in this is the two bright orange cables that is actually directing power to and from the electric motors that drives the vehicle. In the back is where we have the rest of the hybrid horsepower story. This is the hybrid high voltage battery that contributes to the engine horsepower and gives us the overall horsepower rating of the 339 horsepower. This is where it's stored.
What kind of fuel efficiency do you get for your 339 horses? 28 miles per gallon on the highway and 25 miles per gallon in the city.
The reason we get such good gas mileage on this vehicle is the fact that we can only operate the gas engine when it's needed. We can operate solely on electric power, which conserves the gas. Okay, we start the car by just a simple push of the button. We may not hear the engine running because we start out on electric power most of the time once the vehicle's warmed up.
Out on the road, a computer monitors and controls the hybrid power system for maximum efficiency.
As we begin to accelerate, you see the electric motors come in, and we're running solely on electric power at this point. To get the maximum horsepower output, we need to get both the engine, the gas engine, and the electric motors fully engaged. And we just simply step on the throttle, and they automatically come to life.
With a top speed of 131 miles per hour and a 0 to 60 acceleration rate of 5.2 seconds, the Lexus Hybrid can rival most high-performance sports cars on the road today.
I look for the future vehicles to be rated with high horsepower, and hybrid technology will be a standard term.
So technology will provide improved and more efficient engines. But it's safe to say that the way we measure their performance will be the way we've measured our engines for close to 2 centuries, with horsepower.